In the last video, we discussed Cavalier's principle and found the volume of this example that we were working with by slicing in along x is equal to x naught. Now, that was a little arbitrary. Could I have sliced in a different direction? And if so, what would happen? Would I get the same volume? Well, theoretically, I mean, volume is volume. Volume is fixed. It can't change. So let's see if we can see that result mathematically by looking at a different slice. So let's say I slice along the plane y is equal to y0 instead. So if I do that, now this one could be a little bit more interesting to draw, but let's say I am slicing along this plane here, and I can't see that, and I can't see that, but it would look something like this. So as a figure, it would look something like this. This would be the slice, and something like that. Okay, and so I would have this particular slice that would be vertical along my, or vertical on a 2D drawing. So how does that change what we do here? Well, in terms of the area, I still have an integral. It's still going to be of f, but now I'm holding y constant at y naught, so I'm allowing x to range from 0 to 2. Okay, so that should be the area. And then the volume, okay, and then if I compute this in my particular example, so this should be 0 to 2 of 6 minus x squared minus y squared, and then dx. Okay, I believe what I get here is 12 minus 8 thirds y squared minus 2y squared. Okay, and then for volume, again, this is going to be the integral of the area. So this is going to be a of, this one will be a of x, and then, or a of y, I'm sorry, a of y dy. Okay, and y is going to range from 0 to 1. Okay, and so then again, if I do this in my particular example, this will be 0 to 1 of 12 minus 8 thirds, and I could have simplified that, I was just too lazy, minus 2y squared, and then dy. And at the end of the day, when I do all the number crunching, I get 26 over 3. So indeed, I get the same area. So it truly doesn't matter which order you do these in, and in fact the theorem below actually encompasses that. So if we have a region, a rectangle, and we also have a function that is continuous and non-negative, so yes, we do need to verify, or at least mention, justify that our function is continuous and non-negative on R. Then all we have to say is that the integral from a to b and integral from c to d of f of x, y, and this would be dy dx, noting that the first differential corresponds to the innermost integral, and then this is going to equal the integral from c to d of the integral a to b of f of x y, oops, bad handwriting, f of x and y dx dy. Okay, so that's a theorem that you can use as long as you have continuous and non-negative. And then just for us in our language that we're going to use, the integrals that we have above in green, these are called iterated integrals, mainly because you can switch the order of the integrals and still achieve the same result. Okay, but you do need those suppositions of continuous and non-negative. Okay, so takeaway. You can use iterated integrals, okay, and the nice thing about these, at least if you're using Cavalier's method, is that these are easy to compute because these generally are nice continuous functions, so finding the antiderivatives are easy. But the disadvantage, we need continuous, we need non-negative, and you need rectangular regions. Okay. In general, you might not always have these three things. Okay. So what do you do in those cases? And so we'll talk about some of these, but we'll not be able to address all of them yet. Just know that we will hopefully be able to address them by the end of the semester.